Hi everyone, welcome to this channel. If you're new here, my name is Hasan. Let's begin our fourth part of the video series. Today we'll be starting our studies on spherical mirror. I have already completed the video on plane mirror. If you haven't checked those videos, then you can check those by clicking the icon at the top right corner or by clicking the link in the description below. Remember, in order to be good at anything, you need to have a solid fundamental concept, so never ever ignore the fundamentals. I understand student mentality as I am also a student. This video will deal with the fundamentals of spherical mirror. So without wasting time, let's roll the intro. Okay, today we'll be studying kinds of spherical mirror. But before that, I need to tell you that if you want to be a genius in the subject of physics, you need to do one thing. As you can see on the screen, it's written kind of spherical mirror, written in pink background with white color. But beside that, there is a button, a red button. It says subscribe for awesome content. So in order to be genius, you just need to do one thing. Go down and subscribe to this channel and you'll be genius in the subject of physics. No, I'm joking. Okay, that was really a lame joke. So, okay, keeping joke aside, let's start our study on spherical mirror. So let's begin. As you can see, kinds of spherical mirror. There are two kinds of spherical mirror. As you can see, there are two kinds of spherical mirror. One is concave, another is convex. Let's understand what is concave mirror. As you can see on the screen, concave mirror, light comes and hit the inside portion of the cave. So this one. Okay, so the word cave is important. From where it comes, concave. Okay, when light comes and hit the inside part of the cave, then it is known as concave mirror. That kind of mirror is known as concave mirror. That is the opposite part. This part is actually silvered. This part is silvered. So this is known as concave mirror. So the reflecting surface is the inside part of the cave, as you can see. The second type of mirror is just the opposite of concave mirror. So it is known as convex mirror. Okay, light comes and hit this portion, as you can see. Okay, and the opposite portion, this side is silvered. Okay, just remember one, and the opposite is known as convex mirror. If you remember the concave mirror, then the opposite is convex mirror. Simple as that. The important thing is why it is known as spherical mirror. As you can see, I have written it down. Why it is known as spherical mirror? It's known as spherical mirror because these mirrors are cut out from a spherical object or a spherical portion. Let's understand that first. So this is, suppose, a spherical body, hollow spherical body, in which if we silver the outer portion, okay, we polished and silvered the outer portion, and then what we did is we will cut out a portion from this. Okay, so let's cut out a portion from this. If we cut out a portion from this, and I have rubbed off this part, then we are actually getting a mirror, and you can look at this figure and say that this is actually concave mirror, isn't it? So we can say this is concave. Why it is concave mirror? Because light will come and hit the inside part of the cave. So this is known as concave mirror. Now, how to understand convex mirror, how we actually derive convex mirror? Simple, just we do the opposite thing. So this is our spherical body, and this time what we do is polish or silver the inside part of the spherical body. Okay, now what we'll do is we will take a portion from that spherical body to create a mirror known as convex mirror. Now you can see that light comes and hit this portion, that is not the inside part of the cave but the outside part, and therefore it is known as convex mirror. I hope the concept of convex and concave mirror is clear, and why it is known as spherical mirror is clear. Now let's move on to our next concept. Now we'll be learning some of the terms related to spherical mirror, which are very important. Okay, these terms will occur again and again when we'll be studying spherical mirrors. Okay, the first thing, as I have already explained, that spherical mirrors are created from a spherical surface from which we cut out certain portion. Okay, now as you can see, this is the spherical body from which we will be creating the mirror. Now every spherical body has a center, and that is known as the center of the sphere. As you can see it here, the center of the sphere, I have marked it here with C. Now when we create a spherical mirror from this spherical body, then we will get either a concave or a convex mirror according to our polished surface. Okay, now the center of the sphere from where we are actually cutting out and creating the mirror is known as the center of curvature of the mirror. Okay, so we have cut out a mirror, this one, and this is the center of the sphere from where we have cut out the mirror. So this C is known as center of curvature I have written down in pink, you can see. So center of the sphere is also known as the center of curvature of the mirror that we are creating, okay? And it is similar for both concave and convex. Now the next term that we'll be learning is a radius of the sphere. Now the name suggests, again, radius means the radius of the sphere from where we are actually cutting the mirror, okay? So again, if we look at this bigger sphere from where we are creating the mirror, so this has a center, this C, and this is the radius of the sphere. Now when we cut out the mirror from this to this, then this radius is actually this radius, and this radius in terms of spherical mirror is known as radius of curvature. I hope the concept is clear. So the radius of the sphere is known as the radius of curvature of the spherical mirror. Now the next concept that we'll be learning is pole. Now what is pole? It's very simple. Pole is center of the spherical mirror. Very simple. Now I'll explain by drawing it. Suppose this is the mirror that we have cut out from the spherical body, okay? Then the center of the spherical mirror. So this is the mirror. The center of the mirror is known as the pole. I hope the concept is clear. So write it down. Pole is center of the spherical mirror, and I have marked it with pink color. Now let's move on to our next term, that is principal axis. What is principal axis? Now principal axis is the line joining center of curvature and pole, as you can see in the diagram. And this is actually, you can also extend this line backward, but that line is actually joining center of curvature and pole. Therefore this line is known as principal axis. So in short we can say principal axis is the line joining the center of curvature and the pole. I hope the concept is clear. Now the next term that we'll be learning is aperture. Now what is aperture? Look at the diagram. The diagram is very important. In order to understand anything, you need to have a diagram to make things simpler. Now as you can see, it's written that area of the reflecting surface is known as the aperture. Now suppose this is the concave mirror, as you can see. So light will come and hit the inside part of the cave, okay? So the green color that you are seeing is actually the total area on which light comes and reflect. So that area over which light comes and then reflect is known as the aperture. The total area, that is the total green color, is actually the aperture. I hope the concept is clear. Now the next term that we'll be learning is very important and is known as focus or focal point. Okay, it has two names. One is focus, or you can say focal point, but focus is most commonly used. Let's understand this. We have taken this one as a concave mirror. Okay, first of all, understand concave mirror. Now it says that rays parallel to principal axis after reflection passes through a fixed point known as focus. As you can see, this is the black ray, okay, this ray, which is parallel to the principal axis. The principal axis is this one, as you can see. So the rays are parallel to principal axis. It goes and hits the inside part of the cave because it is a concave mirror. After reflection, it obeys the reflection law, that is the angle of incidence is equal to the angle of reflection. As you can see, it is marked with green color and the normal is marked with green color. Okay, we know that the normal to a spherical surface always passes through the center of curvature, and I have explained this while I was explaining a concept related to plane mirror in my part 1 video. Okay, so I hope you have gone through that video. So that's the normal. Angle I is equal to angle R, and then after reflection it passes through a point and we say that that point is focus. How many be the rays, that doesn't matter, because any rays that are parallel. Now let's analyze this second ray that is parallel to the principal axis. You'll see that again after reflection it will pass through that same point. Even if I take another ray here, another ray here, and it is parallel to the principal axis, then no matter where the rays are, if the rays are parallel to principal axis, after reflection it will pass through a common fixed point, and that point is known as focus. Okay, I hope the concept is clear. Now let's understand what do you mean by converging mirror. If we analyze, this is the principal axis, this is the mirror, so this is a concave mirror. So we saw that light rays, parallel light rays, after reflection, what happens? It converges towards a point, isn't it? Converges towards a point. Therefore, since the light rays are converging towards a point, this is known as converging mirror. I hope the concept is clear. So they can ask you in objective question in NEET, which mirror is known as converging mirror? You need to say concave mirror is converging mirror. Now let's move on. If we analyze convex mirror, same thing. Any rays parallel to principal axis after reflection appears to meet at a fixed point, and that is known as focus. That fixed point is known as focus. Okay, let's see. This is our ray 1, this is our ray 2, which are parallel to principal axis. After reflection, it follows the reflection law. that is angle I is equal to angle R, and you can see I have drawn the normal, and that normal is passing through the center of curvature, as I have already told that normal to a spherical surface always passes through the center. Okay, so after reflection we can see that this is the blue ray after reflection, and the second ray after reflection it went this side. This is the blue ray. Okay, but when we look at this mirror, it seems as if those rays are coming from a certain point. Okay, if we extend those points, we will see that it is coming from a certain point. It appears, it is not actual, but it appears as if those rays are coming from a certain point, and that fixed point is actually the focus. So how many rays we may take? If those rays are parallel to the principal axis, after reflection it will appear to come from a fixed point. It will reflect like this. It will reflect like this for these cases. Okay, I hope the concept of focus in case of convex mirror is clear. Now I haven't told one thing, that in case of concave mirror we can see that the rays are coming in this direction and falling on the mirror, and the center is also in this direction or in this part of the mirror. When I take convex mirror, okay, the rays are coming and hitting this side, but the center of curvature will be inside, obviously, because that's the inside part of the sphere, and we know that center lies inside the sphere, so center of curvature will be here. Okay, I hope the concept is clear. If it is not clear, then pause the video, look at the definition that I have written about focus, and then understand it again. Let's understand why it is known as diverging mirror. So let me rub this portion. Okay, now let's see. This is our convex mirror. This is the principal axis. This is our pole. This is our center of curvature. Now light rays parallel to principal axis falls on the mirror, and we see that it diverges. Rays coming and hitting the mirror, and then it diverges. Okay, therefore since the rays after reflection diverges away, therefore it is known as diverging mirror. So these are very important things, and you need to note these because they may ask you in objective which mirror is known as diverging mirror. So convex mirror is also known as diverging mirror. Now let's understand one important point about focus. Okay, the focus of a convex mirror, we are now discussing convex mirror, this one. So this is our convex mirror. The focus of a convex mirror is imaginary. Why it is imaginary? Because rays do not meet at that point. It appears to meet. So everything is happening virtually. Therefore, the focus of convex mirror is also known as imaginary focus. So they can ask you in objective, focus in convex mirror is real or imaginary? And we know that convex mirror, the rays appear to meet at that point, but it is not actual meeting. Therefore, that focus, that point is known as imaginary focus. But in case of concave mirror, if you look at concave mirror, the focus is real focus. Now let's look at the diagram. You'll understand why. Because the rays that are parallel to the principal axis after reflection, you can see that it is passing through a real point. Actual rays are passing through that point, therefore this is known as actual focus. But in case of convex mirror, actual rays are not passing through that point, it is happening virtually, therefore this is known as imaginary focus. So very important, write it down. The focus of convex mirror is an imaginary focus, whereas the focus of concave mirror is a real focus. Now let's move into our next part, that is focal length. So what is focal length? Let's analyze. Distance from the pole to focus is known as focal length. You can see it in the diagram. We know this is pole, we know this is focus, so the distance between focus and pole is known as focal length. Now let's understand what is the relationship between radius of curvature, capital R, and focal length, denoted by small f. It says that focal length is equal to half of radius of curvature. But this is not always true. It is true only when it meets the condition. So this condition is very important. If spherical mirror is small, or parallel rays are very close to the principal axis, okay, then only this thing will hold. That is, if we say that the mirror is very small, okay, then we will get this relation, that f is equal to r by 2. Or if this is the mirror and if the parallel rays that are coming are very close to the principal axis, then we will get f is equal to r by 2. And in NEET, most of the time this relation holds good, and questions are asked from this relation only. But if the question is tough and they ask questions related to when is this relation holds good, then you need to remember these conditions, that the spherical mirror should be small, or the rays parallel should be very close to the principal axis, and if these conditions are not met, then f has different value. Okay, it has a different relation, and we will derive that, don't worry. Okay, so let's follow. So if we move on and let's analyze, if this condition is not met, then what will happen? That is, spherical mirror is not small, or the parallel rays are not very close to the principal axis. Now let's see. This is our ray that is going parallel to the principal axis, okay, and it goes and hits the concave mirror. This is a concave mirror, and it follows the laws of reflection, that is angle I is equal to angle R, and then it passes through the common point F. Very simple. Okay, now let's analyze. If we know that angle I is theta, I have written down here I is equal to theta. Suppose we have said that, suppose, then angle of reflection small r will also be equal to theta. If this is theta, then this will also be theta, isn't it? This angle will also be theta. This is known as alternate angles. If this is theta, and we know that angle R is also theta, therefore the triangle, let me write the name of the triangle. We can say triangle COF. This is O, okay, this is O. COF is actually isosceles triangle, isn't it? Why? Now let's analyze why it is isosceles triangle. Now we can see that angle C in this triangle, angle C is theta, and we can also see that angle O is also theta, which is nothing but angle of reflection. Okay, so since we know that when a triangle, two angles are equal, then we say that two sides are equal. Okay, and we say that this is isosceles triangle. Simple as that. Now there is a property of isosceles triangle. Let's understand that property first. We can see that this is the isosceles triangle, and this side, let me give some name, A, B, C. So you can see that AB is equal to AC. Why? Because angle B is equal to angle C is equal to theta. Therefore it's isosceles triangle. Whenever we draw a 90-degree line over BC, that is the line that is sharing the same angle. Okay, if we draw a perpendicular line from the opposite vertex on the line that is sharing the same angle, then this line gets divided into equal parts. So you can say that if you write BM, we can say that BM will become equal to MC. Okay, this is one of the property. Now let's apply this property here in this triangle, that is triangle COF. So what we did, this is the triangle, let me pick another color. This is the triangle theta, this is again triangle theta, and this is the opposite vertex F. If we draw a line perpendicular to that line that is sharing the same angle theta and theta, 90 degree, then we can say that, and if we name this as M, we can say that CM is actually MO, isn't it? From the property of isosceles triangle. Okay, now let's analyze. If CM is equal to MO, then what will happen? Now let's understand how much will be cos theta. Cos theta will be R by 2x. How? We know that cos theta is equal to base by hypotenuse, isn't it? So if you look into the triangle, that is triangle CFM, okay, then we can say that cos theta, the base here will be, if we take theta as a reference, then base will be CM divided by hypotenuse. Hypotenuse is x. I have marked it in the diagram. Okay, now this is simple. Now let's understand what is CM. How much will be CM? We know that CO is nothing but radius of curvature. Look at the diagram. Okay, and CO here is actually CM plus MO. Okay, and from the property of isosceles triangle, we have said that CM is equal to MO. I have already derived that. Look at the diagram of the property of isosceles triangle. Here I have derived CM is equal to MO. And therefore, you can say that R, because CO is equal to R, is equal to 2CM. Therefore, you can say CM is equal to R by 2, isn't it? So from there, we have said that CM is equal to R by 2. Once that is clear, we will just substitute the value of CM here. Okay, so R by 2, and we know that hypotenuse is x. So we got that cos theta is this one, R by 2x. Okay, from there we will calculate x. Okay, so x is equal to R by 2 cos theta. Now why we have calculated x? Because if we calculate x, then only we can find out focal length, small f. Now let's move on. But before that, the two assumption was, I said that the relationship between capital R and f is that r by 2 is focal length, isn't it? But for this to hold, we need to have two conditions. That is, the rays that are parallel to the principal axis should be very close to the principal axis, or the mirror, spherical mirror, should be small. If the rays are very close to the principal axis, let me draw. Okay, if this is the principal axis, if the rays are very close to the principal axis, if this is the focus, then the theta angle that is produced will be very small, isn't it? Or else if the mirror is also very small, then also we'll see that the after reflection, the angle theta will be very small. If angle is very small, we know from the property of trigonometry, we know that cos theta is equal to 1 when theta tends to 0. That is, theta is very small. Then cos theta is always small, because we know cos 0 is equal to 1. So when theta tends to 0, we have the cos value as 1. Okay. So very simple now. Just find the value of x by putting the value of cos theta as 1, because we know that theta is, we have assumed that the rays are very close to the principal axis or the mirror is small. So theta is tending to 0 degree, therefore cos theta will be 1. If we put the value of cos theta as 1, we will get x is equal to r by 2. Simple as that. Therefore focal length, now look at the diagram. What is focal length? Focal length is the distance between focus and pole. If you look into this diagram, let me choose a different color. This is capital R and this is focal length, small f. In order to find focal length, f should be equal to r minus x, isn't it? So f is equal to r minus x, and we have already found out the value of x. So let's put the value of focal length r minus x. We know r is equal to radius of curvature minus this x is equal to r by 2 cos theta. So if we put cos theta as 1, if theta is small, as most of our cases, then we will get f is equal to r by 2. Simple. If cos theta is 1, that is theta is small. But if certain special cases are given where theta is not small, then you need to use the formula for focal length. F is equal to r minus r by 2 cos theta. Okay, maybe somewhere at the end of the video I'll give you a question where I'll be utilizing this formula in order to solve a numerical. Okay, so I hope the concept is clear about focal length. Once it is clear, now we'll be moving on to our next concept, how to measure this focal length and what is the sign convention. So let's move on. Now how to measure the focal length, but before that we need to understand the sign convention. This is the part where students confuse the most. Okay, understand the sign convention. It's very simple. You just need to understand what I'm trying to say. Just concentrate for once and it will be clear, and then you'll never make mistakes regarding signs in ray optics. Okay, first point is very important. All distances are measured from the pole. So we can say that pole is taken as origin. Okay, so whatever may be the case, we will start our calculation from the pole. So we can say that pole is actually the origin. Simple as that. Now whatever may be the mirror, whether it is a concave or a convex mirror, the rules are same for both the mirror. The second point says the direction of incident ray is taken as positive. Suppose if the incident ray is in this direction, okay, then this direction is taken as positive. Then the opposite direction, that is the third point, will be taken as negative. Simple as that. Let's analyze. Suppose this is our concave mirror. Okay, this is our pole. So if rays are incident in this way, then this direction is taken as positive and opposite direction will be taken as negative. If this is the concave mirror, okay, and incident rays are coming and hitting the mirror this side, then this side is taken as positive and the opposite direction will be taken as negative. I hope the concept is clear. This is for concave mirror. Now let's look at convex mirror in order to make things more clear. Suppose this is our convex mirror, principal axis, this is our pole. So the incident ray will come from this side, so therefore this direction will be taken as positive, so the opposite direction will be taken as negative. I hope the concept is clear now. Once this is clear, now we are ready to find out the direction or the sign of focal length for different mirrors. First analyze concave mirror. Okay, so the incident ray is in this direction, therefore this direction will be taken as positive and the direction opposite to this will be taken as negative. Okay, Now we know that pole is actually the origin, that we will be starting our calculation from pole only. So focal length, so we know that this is our focal length from focus to pole, that is focal length. Now in order to measure the focal length, we need to go from pole to this side in this direction, that is opposite to the direction of incident ray. Therefore we can say that focal length of concave mirror is always negative. Always. You need to understand this. Now let's analyze a different case. Like again, this is our concave mirror, okay, and rays will come and incident here, so this will be taken as positive direction, okay. So the opposite direction will be taken as negative direction, isn't it? So we know this is the center of curvature, this is the focus, it should be taken as capital F. So this length is actually from the pole to the focus is focal length. So we are measuring from pole to focus, which is actually opposite to the direction of incident ray, therefore it will be negative. So you can see that the focal length for concave mirror is always negative. You need to remember this. They can ask you this in objective, okay. So you need to remember that the focal length of a concave mirror is always negative, whatever may be the case, okay. Now let's look into our convex mirror concept. Again, we will apply the same concept here. For the convex mirror, the direction of incident ray is taken as positive, so this direction will be taken as positive. Therefore any direction that is opposite to incident ray will be taken as negative. Now this is the focus, capital F. So the focal length, this is our pole, okay. So the focal length is this one, and we'll be starting our measurement from the pole. So this is our focal length. So in order to measure the focal length, we need to move in this direction, which is same as the direction of incident ray, isn't it? So the incident ray is in this direction, positive, and for focal length we are moving in this direction, so positive. Therefore for convex mirror, focal length is always positive. Very important. Remember that focal length for convex mirror is always positive and focal length for concave mirror is always negative. So this is the concept of sign convention and how you need to apply that. Another thing for sign convention I need to write here that I've left out, but I'll be using this concept when I'll be teaching the concept of magnification. So that is when we move up from principal axis, we will take measurement as positive, okay, and when we move down, we will take it as negative. So suppose this is our mirror, this is the principal axis. If we move up, then we will take the measurement as positive, and if you move down, we will take it as negative. So this is what I'm trying to say. So I'll use this concept when I'll be teaching you the concept of magnification, okay. So this is all about the sign convention. So the only last part that is left about the terms related to spherical mirror is focal plane. So let's understand what is focal plane. So focal plane is very simple. Look at the diagram and things will be easy. We know that two rays parallel to the principal axis, after reflection, what happens? It passes through a fixed point and that point is known as focus. But if the two rays are parallel and that are not parallel to principal axis, like as you can see, these are ray 1 and ray 2. These two rays are parallel, but they are not parallel to principal axis. Then what will happen? Then after reflection, they will meet at a common point. Yes, they will obviously meet at a common point, and that point will lie on a plane, and that plane is known as focal plane. You can see the diagram that this is the focus, okay, that I'm drawing, and the pink color, that point is also lying on the same line of the focus, that is the meeting point of the two parallel lines. And the blue color that I have drawn, that plane, if we see that plane, then we will see that focus and the point of intersection all lie in that same plane, and that plane is known as focal plane. I hope the diagram is clear. It's very difficult to explain things in statements sometime, but the diagram makes things much more easier. So this is for concave mirror. So this happens only when the rays are parallel but are not parallel to principal axis. Same is the case for convex mirror. Let's see, when two rays, we can see that these two rays are parallel to each other. After reflection, what happens? They meet at a point, at a common point, and that point lie on a plane containing the focus. Therefore that plane is known as focal plane, because that plane contains the focus. and it is also lying on that same plane. Therefore, that plane is known as focal plane. Very simple. So this is the concept of focal plane. I hope the concept is clear. So let's look into this final question, and I'll wrap up the video with this question. So let's see. It says a concave mirror. So this is a concave mirror, and it's given that the radius of curvature is 5 centimeter. Very good. So this distance, that is the radius of curvature, is the distance between center of curvature to pole. So this is radius of curvature. It's given to be 5 centimeter. Now you need to find the focal length. This is asked, and it is given that the parallel rays are at a distance of 4 centimeter. Okay, that are hitting the spherical mirror or the concave mirror. So how to find this? Now if you directly say that, your answer will be, we know that focal length is r by 2 for most of the cases, then it will be 2.5 centimeter. If you write this, then this is absolutely wrong. Why? Because look at the radius of the curvature, it is 5 centimeter, and look at the distance of the parallel rays, it is 4 centimeters. So it's comparable. It's not very close to the principal axis, isn't it? I said that f is equal to r by 2 is only applicable when parallel rays are very close to the principal axis or the spherical mirror is very small. But both of the cases are not satisfied here. So we know that when these cases are not satisfied, then focal length is given by f is equal to r minus x, where x is nothing but r by 2 cos theta, where this theta is actually angle of incidence, isn't it? I was theta. Now you need to use this formula to solve this question. So very simple. Let's redraw this a little bit. We can bring this distance here, like it will be 4 centimeter, and this is actually the radius of curvature, that is 5 centimeter. So this angle is theta. We know that any line that passes through the center of the curvature is actually the normal, because we know the normal of a spherical surface always passes through the center of curvature. I've already discussed this. Therefore, we can see that this is 4 centimeter, this is 5 centimeter, this is 90 degrees. So this is a right angle triangle. By using Pythagoras theorem, we can say that this is 3 centimeter. Simple as that. So it's done. Now how to apply or how to find f? F is equal to r minus r by 2 cos theta. Now we need to find the value of cos theta. We know cos theta is equal to base by hypotenuse. Now base here is 3 centimeter and hypotenuse here is 5 centimeter. Just put the value. You know the value of r is 5 centimeter. Just take 5 as common. 1 minus, put the value of cos theta. Okay, so it will be 5, 1 minus 5 by 6. So if you solve this, we will get 5 by 6. Okay, so this is the focal length. Simple as that. This is how you need to find the focal length when either theta is given. Listen to this, very important. Whenever this distance is given, or whenever this theta is given in the question and you were asked to find focal length, then you never use this formula, f is equal to r by 2. Always use this formula. Okay, I hope the concept is clear. So this is all for this video. If you enjoyed this video, then please give it a thumbs up, and if you haven't subscribed to this channel, then please consider doing so. Till next time, enjoy your studies and build your concept, and I will catch you all in my next video. Bye bye.